really, there's only one homework that's upcoming, and that is the homework on distribution of sample means. That is due tomorrow. We're going to be finishing it today in class. There's about 12 questions. Actually, there's 10 questions. I'll remove 2 of them. I'll remove questions 10 and 12, so there's only 10 questions. So make sure you get those done by tomorrow. Besides for that, that's really all that's expected for this class so far. It's starting off pretty light after coming back from the spring break. So that's pretty much all I have there. So does anyone have any questions for me before we get started? If not, so yeah, some of you might have noticed I changed 60 to 50 because when I worked out the problem again, I realized it didn't go in the right direction that I wanted it to. We would still get answers, but somehow the problem changes whenever you get a mean that's positive versus a mean that's negative. And I want to get a negative mean to have a similar conclusion as one of your homework problems. So changing 60 to 50 will accomplish exactly that. So we're going to redo this problem. And I also did make a mistake on, I think it was part D of this problem as well when I did it. So just to get rid of those 2 mistakes outright, I'll just, I think I'll put 100 instead of 0 in part D. I wasn't supposed to put 100 for wherever I put it at. I know I made a mistake on part D of this problem as well. So we're just going to start over with this problem with 50 and make sure to iron out the loose ends here. So we're going to do the problem again, just as a reminder of what I did last time. The problem really does start off the same though. Well, let's just reconstruct the situation. The situation is there's a deck of 52 cards. You win some money if you pick up a card that you're able to call off. So if you say, I'm going to pick up the ace of spades, and you pick up the ace of spades, you'll get $50. You don't do that, then you lose $1. And so we're going to really dive into, is it worth continuing to do this again and again and again? Is it better for you from a probability standpoint to keep trying to pull a card again and again, of course, after the card you draw is shuffled back in, so it is replaced? Is this better odds or worse odds? Because intuitively you would think it's better odds. So let's find out. So what we did last time is still the same. The chances of drawing the specific card, you have a 1 out of 52 chance. And the chances of not drawing the right card are the remaining 51 cards working against you. And so the numbers you had there were already right. So we'll just go ahead and remind ourselves of what these 2 numbers were. 0.0192 and 0.9808. So these are the same numbers from last time. So far, nothing really changes. The mean and the standard deviation, they are going to change. So since we have a table of values, this means we would find the mean and the standard deviation. So this is the mean and the standard deviation of the random variable. Before we were talking about the mean and standard deviation of the sample means, but normally we find that when we're given a sample size. Remember what we talked about before, when we're given a sample size, it's normally when this introduction of a lowercase n is involved. We don't have that yet. We're just going to figure out the mean and standard deviation of a table of, well, values and their corresponding probabilities. And to do that, what I did last time, so it's the same process. We go to Stat and Edit. This is when we use the one variable statistics where there's 2 columns working together. This is like the weighted mean stuff that we did. And this one's going to be a very easy table. 50 and -1 for the first column. 0.0192 and 0.9808 for the second column. There's not really much else to put. Quit out of that and go to one variable statistics. But if you press enter here, the calculator is not going to know, or if you have the fancier calculator, if it just says L1 and doesn't say L2, your calculator is not going to know that L1 and L2 are related in this problem. So we need to add L1, comma, L2. And I believe I wrote that in the notes last time. So I'm going to write that again, just as a reminder. One variable statistics, just to remind everyone where this is coming from. L1, comma, L2. And we get a mean, not a mean of the sample means. This is a straight up mean of the probabilities. So this would be your standard mean, because we don't have a sample size. So we get a new mean of negative 0.0208. And I wanted a negative for this mean. It works out much differently when you have a negative for the mean. So that's what I really wanted. That's why I changed 60 to 50. And we can also figure out that the standard deviation is 6.9986. So this will definitely work out the way I want it to. So we get these values so far. And we're going to go ahead and now introduce a sample size, n equals 100, which means now we can look at the mean and the standard deviation of the sample means, now that we have a sample size. Mainly this helps us find the standard deviation. So the mean of the sample means is the mean of, well, the population, which we found to be negative 0.0208. And the standard deviation of the sample means, well, there's a formula for that. So I'm going to point out the person on the who's busy on the laptop. What is the formula for that? Got to make sure you're on the laptop for the right reasons. Well, I have the formula right here. So the standard deviation of the sample means, just sigma over the square root of m. It's the standard deviation divided by the square root of the sample size, n. And so we figured out that the standard deviation is 6.9986. That's divided by the square root of 100. Square root of 100 is just 10. And dividing by 10 simply moves the decimal over to the left one place. So this would be 0.69986. They might get you to round it to maybe 4 decimal places, but you get the idea. You get a mean of the sample means and a standard deviation of the sample means by just following those formulas. And generally in every problem, you need to figure out the mean and the standard deviation of the sample means in order to determine these corresponding probabilities. And we talked about how to do this in the calculator. So when the sample mean is greater than 0, this is the probability when the sample mean is greater than 0. I think last time I put 100, and I should not have put 100. You wrote down the notes from before, so just ignore that. Probably me rushing. So I told everybody how to do this in the calculator. This is the normal CDF command in the calculator. And what did we put in this command in the calculator? The lower value, the upper value, the mean, which is the mean of the sample means, and the standard deviation of the sample means. So let's see how well you all have retained the last Monday's lecture. What are the lower and upper values here? What do we put? What's that?
1 and 52.
1 and 52? Where are you getting those numbers from? Oh, we're over that. We got all the information we needed from the cards. What would be the lower value here based off of everything I wrote here?
0.
0. That's it. Lower and upper are strictly based off of the inequality. That's it. The inequality tells you everything you need to know. We've already extracted everything we need to from the premise of the problem. So the inequality says that the lowest number is 0, and the highest number, well, we're looking at the sample means. If the sample mean is greater than 0, well, greater than 0, what numbers are greater than 0? 1, 2, 3, 4. What's the largest number greater than 0?
10,000.
Well, 10,000, well, so technically it's infinity, and if you think about it theoretically, but we can't tell the calculator infinity. So we have to sort of trick the calculator. So we pick something very large, 10,000. Again, the same process. So as I said last time, we picked 10,000 by default. Now, if you put 100,000, probably if you put 1,000, it probably won't change anything. We just need to give it a fairly large number just to trick the calculator. And the margin of error is going to be so small that it's not going to be deterministic through the calculator. But from here, we can go ahead and apply the mean, which is negative 0.0208. And that negative is very important here. It gives us a much different conclusion. And then 0.69986. And from all of this, we go straight to the calculator, plug it in directly, and we're done. Again, I had 100 here, I think, last time, and it definitely should not have been 100. It should have been 0. So we'll fix that here. So just to remember, if you're following along with me, I do have the tutorial in the notes, but second in vars to pull up the distribution menu. We go down to normal CDF. That's pretty much the main command we use here. And then we can go ahead and type in 0, 10,000, negative 0.2, well, 0.2, 0.8, 0.69986. So we get a probability of 0.4881, rounded to 4 decimal places. So the way we interpret this, the sample mean being greater than 0, well, the sample mean is referring to, I mean, if you break down the problem, it's ultimately referring to how much money you're going to make back. And so you're asking yourself, all right, am I going to leave this gambling site with a profit or a loss? And it's saying that if you draw a card 100 times, you got less than a 50-50 chance of leaving with a positive amount. You have about a 48% chance of doing so, of leaving there with something positive. And I say something positive because this is greater than 0. Greater than 0 meaning you make more than $0. So that's what it's referring to. Does anyone have any questions before we look at part E? All right, part E. Notice how they change. Well, the sample mean is greater than 0. Okay, cool, the same inequality. For n is equal to 200. I thought n was 100. Say n is 200 now. How does that change things? N is 200 now.
The standard deviation.
It does change the standard deviation. That's right. The standard deviation, the one we used up here, that 0.69986, can't use it anymore. Notice that standard deviation, we divided by the square root of the sample size. But that was the sample size of 100. They just gave us a new sample size. So guess what? We have to find a new standard deviation. So you are exactly right. This is, the mean stays the same. The mean is not based off of the sample size. So the mean is fine. That's still negative 0.0208. But the standard deviation, well, I'm going to just rewrite the formula just to remind everyone. The old standard deviation, the population one, was 6.9986 divided by the square root of now 200 instead of 100 because n is now 200. So we can figure that out right fast. 6.9986 divided by the square root of 200. And so we get a smaller standard deviation from what we had before. 494.9. So that's just.
You put 6.9. Oh, wait. Never mind.
Got it?
Yeah, I used the answer that we got for 100 instead of the 6.9.
Yeah, we want to use the standard deviation of the population, which is what we found in part B. And so from here, and this makes sense as you do more trials, remember the standard deviation of your sample means is called the standard error. And your error is going to be much less the more trials you do, because you'll find more values centered towards the middle as you do more trials. This is off of the central limit theorem, I believe, that we talked about last time in class. But from here, all of that rambling is nice and everything, but from here the computation's very easy. We do normal CDF again. And yet again, we need to put in the lower, the upper, the mean, and the standard deviation. Well, guess what? The lower and the upper stay the same. In fact, the mean does as well, because it's the same inequality, which tells us that the lower would be 0 and the upper would be 10,000. The mean is still negative 0.028. Wait, 0.8. Forgot a 0. Let's fix that right fast. 0.8. I'm out of space, so let's erase that and throw in one more value of the new standard deviation of the sample means that we found, 0.4949. Close that off. Now, if you're good with the calculator, you can just press second and enter. Second and enter. And you can just go back and change 4949. Our new probability is 0.4832. So our probability in part D decreased in part E when we did more trials. And that's an interesting observation to make. What about do the same problem in part F, but Now n is 1,000. Now, as you would imagine, we're going to do the same process. We have to find a new, well, not mean of the sample means. That stays the same because that's not based off of n. We need to find a new standard deviation of the sample means, like we did before. It works out the same exact way as the previous problem. 6.9986, the population standard deviation, divided by the square root of 1,000, which is some number. .9986 divided by square root of 1,000. So our standard error decreases as we increase the number of trials. I'll write it this way so I can have room to write the new probability right beneath it. So the new probability greater than 0 is still the same inequality. And with having the same inequality, that means that the lower and the upper are not going to change because the lower and the upper are based solely off of the inequality. So that's 0. And we're using 10,000 as a default for the upper. Again, using 100,000, a million, anything higher is fine. Negative 0.0208. And our new standard deviation, which is 0.2213. So let's figure out what this comes out to be. Again, I'm just going to use second and enter a few times. 2213. 4626. So a thought for a gambler, normally the gambler's curse is you lose a lot of money and your thought process is, I will gamble some more to earn the money back that I lost. So this is looking at really what happens from a probability standpoint. Does your likelihood increase the more times you play? And from seeing all of these probabilities, if you draw 100 cards versus if you draw 200 cards versus if you draw 1,000 cards, your chances of earning a profit decrease, which sounds kind of weird because you think more times to play. If you draw the right card, you get $50 back, and all you do is lose $1. It seems very innocent because you could do this 50 times, and if you win, then you're back at 0. So, but this does illustrate that your odds decrease. As n increases. So for any of you who are out there wanting to gamble and you ever think to yourself, all I have to do is play more to win the money back that I lost, it's not going to work out for you from a probability standpoint. The more times you play, you actually run a risk of losing more money and having less odds of making your money back. And casinos make, well, to be frank, they make damn sure that you're going to lose money. They do stuff like this a lot more than you think. Okay, so yeah, that's pretty much all I have for this problem and this section, unless anyone has any questions otherwise. Okay, well, that concludes this section. So this homework is due tomorrow. So make sure you do this section. Of course, email me. I already have one person, or Actually, a few people email me already. So again, I try to knock those emails out fairly quickly before I go to bed. If I get them before 8 o'clock, as you all know. So email me if you have any questions. I think there's one on there that's kind of tricky. And it's okay to email me if you can't figure it out. But let's go ahead and move on to the next section. And this is viewing, well, not distribution of the sample means, but distribution of the sample proportions. So we've actually been talking about proportions and probability already. Now, remember, the whole chapter is centered around distribution of a bunch of samples. We have a bunch of samples. You go out and you interview 10 people about their heights. And then you think, all right, one sample is not good enough. I'll go out and interview another 10 people about their heights and another 10 people about their heights. And you keep doing that again and again and again. And for each sample, you can collect whatever information you want about them. Normally, the most intuitive would be figuring out the mean and the standard deviation for each one of those, and then taking those means and then further applying statistical analysis on those means. Hence the mean and the standard deviation of these sample means. Something else you can do, though, with that same example in mind, is do that for the proportions, proportions of each sample. Now, the sample proportion here, this definition, well, the sample proportion, which we denote by, informally, it's called p hat. So you might hear me call it p hat. It's just p with this, what's a caret symbol, but we call it p hat. And this this formal definition represents the informal idea that the proportion of something occurring can be figured out by the number of times the thing happens divided by the total number of occurrences. If there's 100 red balls in a bag, or if there's 200 balls in a bag, and there's 100 red balls in the bag, what's the chances of pulling a red ball? It's 100 divided by 200. This is the same idea. It's just the number of occurrences for that item divided by the total number of occurrences in general. And we've seen this before. It's a very intuitive idea. So notice X is the number of individuals with the specific characteristic. So how many times that specific thing occurs. And N, lowercase n, is always denoted as the sample size, which makes sense. But we can generalize, well, these proportions rather. For each sample that we take, we can figure out, based off of that sample analysis, we can figure out each proportion. So the likelihood, if we went out and sampled 10 people on this thing, how many of them voted in this way, or how many of them said this thing? That would give us a proportion. We get another sample. How many people voted this way? How many people said this thing? We get another proportion. These proportions, since we have varying proportions, we can look at that. We can look at the distribution of these proportions the same way we did with the means. Now, we get there's some characteristics that we get here of this distribution, because there's all of these proportions floating around. So for the sampling distribution of p hat, we get that the shape is approximately normal, or we get a normal distribution, provided two things occur. We need the sample size to be less than or equal to 5% of the population size. Capital N is the population size. That's one thing we need. And the other thing we need, which is the more important one, is we need this specific product here to be greater than or equal to 10. If those two things happen, we get that the sampling distribution is approximately normal. What happens when we have normality? That means we can pretty much use the calculator for the normal CDF. That's why we like normality so much. We get to throw it straight into the calculator. Before, that would have been, we get to throw it straight onto the table, but we get to use the calculator now. And we get new formulas. We get new formulas here. The mean of, not the sampling means, but it's not the mean of the sample means anymore, it's the mean of the sampling distribution of p hat, or the sample proportions. So it's not the mean of the sample means, it's the mean of the sample proportions. But again, with the verbose terminology comes the simplicity of the association here. The mean is the probability, or the proportion. The mean is the proportion. There's no computation to it. They normally give you the proportion, and you just immediately say, that's the mean. It's that easy. The standard deviation has a slightly more computational feel. And again, it might be hard to see. This is mu of p hat. Oops. Second. P hat. And this is sigma of p hat, because we're finding the mean of the sample proportion and the standard deviation of the sample proportion. If we were figuring out the mean and the standard deviation of the sample means, we would use x bar. And so notice that these formulas are predicated off of two values. We need, well, for one of these, we need the sample size. And for both of these, we need the proportion. So let's talk about at least the, I suppose, the shape of the distribution, how we would go about looking at this, given n is 1010 and the proportion is 0.84 or 84%. They also give us that the size of the population is 25,000. Now, obviously, what's given, I'll just rewrite this. So these two are obvious, and what they also give us is that capital N is 25,000. That's the one that's not as explicit. So to prove, we're trying to figure out the shape of the sampling distribution of the sample proportion. That's what it's asking us to do. Describe the sampling distribution of the sampling proportion. It means we have to do two things. We need to show that lowercase n is less than or equal to 0.05 times capital N. And then two, we need to show that n times p times 1 minus p is greater than or equal to 10. This is just straight from the definition that's right above it. So we have all the numbers. We have all the numbers here. It's legitimately just plug and see what happens. Plug in, see what happens. So lowercase n is 1010. It's less than or equal to 0.05 times 25,000. And so we're figuring out 5% of 25,000. That's it. 0.05 times 25,000. We get 1250. So we get a true statement. If we would have gotten a false statement, we stop everything and say, we do not get approximately normal, because it would have failed one of the conditions. So instead, we got something that's true. And normally this condition always holds, just rule of thumb. They normally give you this one kind of for free. It's the other one that may be a toss-up, but we do have all the numbers that we need. 1010 times p, which is 0.84, 1 minus 0.84. We need to show that this is greater than or equal to 10. If it is, then we get approximately normal. So this is, again, just something we plug straight into the calculator. 1 minus 0.84. And that's it. We get a true statement because obviously that's greater than or equal to 10. So in both conditions, check and check. What do we conclude? And the 3 dots like this in a triangle, that's symbolic for we conclude that. Since I'm running out of room here. So we conclude that the distribution is approximately normal. That's it. That's all we have to do. It's just 2 computations. If one of those 2 fail, then we prove, well, the opposite. The distribution would not be absolutely normal. Does anyone have any questions about this? Caitlin, do you have any questions about this? Okay, so because of this variability of the sample proportions, remember we had variability of the sample means, so we treated the sample means as a random variable. And more so, we treated it as a normal random variable in most situations, which meant we could use that normal CDF command in the calculator. We could do the same thing for the proportions. And this is contingent upon if we get approximate normality based off of these 2 conditions up here. So, for example, 2, so ultimately what this alludes to is we're going to be doing the same stuff that we did in the previous section, but with different numbers. And to show this, so they give us a sample size, 1,460. They give us the population size, and they give us the proportion. They want us to determine the mean and the standard deviation of the sampling distribution of p hat, which is the sampling proportion. So they want us to figure out the mean of the sampling proportion. Notice I'm not using X bar anymore because I'm not finding the mean of the sample means. So mean, we would use X bar. Here we're trying to figure out everything for p hat, which is the sampling proportion. So I think to myself, okay, well, what's that formula again? So it's right at the top of the screen here. It's just equal to, oh, the proportion, which is p, which it tells us is 0.42. That's it for the mean. It's that simple. Now, the standard deviation of the sample proportion is a little bit more convoluted. It is the square root of p, which is 0.42, times 1 minus 0.42, divided by the sample size, which was given to be 1,460. So as long as you can plug this correctly into the calculator, then you'll get the right standard deviation. Now, the way to type this in the calculator, type it in like this. So, 2. This will actually be fine. That'll actually be fine. 0.0129. So that's what we get. So notice how we get the mean and the standard deviation using different formulas based off of different context. However, the way we proceed once we get these newly acquired means and standard deviations of the simple proportion, then we end up getting problems. The probability of obtaining 657 or more. Well, guess what 657 or more corresponds to? Probability, I'm going to leave a little space here, or more than 657. That's the inequality that we get. But the symbolism that we use, instead of x bar, I want to use p hat, because we're dealing with sample proportions. That is the random variable. So this is when the proportion is greater than 657. But we already said that we can treat the sample proportion as a normal random variable. And because we can do that, because of this assumption of normality, this means we get to throw this into normal CDF. Which still means same thing as before. We find a lower and upper, and we also give the mean and the standard deviation. So let's give a crack at the lower and the upper.
Would 657 be the lower?
Yeah, 657 is the lower. What's the upper?
A number maybe?
Yeah, just make up a number. Just make up a large number. Yeah, 10,000. I figured let's just pick something and keep it default. And then we can throw in the mean, 0.42, and then the standard deviation, 0.0129. Five seconds. Zero, one, two. I got this straight from the book. That shouldn't be 0. Oh, that's wrong. Wrong section. What am I missing here? I got this one straight from the book. Yeah, it's number 14. Up 657 or more, I'm supposed to get 0.0102. What am I missing? Yeah, we did not get that. What am I doing here? What is the probability of obtaining 657 or more individuals? What about if we increase 10,000 to something much larger? Nope. No dice. I think that was worth a shot. So random sample size of size n is equal to 1460. I could have sworn I always do problems before class. What am I missing here? Okay, I did that. Make sure I typed the problem down correctly. A simple random sample size of n is equal to 1460 is obtained from a population size. We don't even use capital N in this problem. And whose population proportion with a specific thing is 0.42. Typed it down correctly. What is the probability of blah, 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 657? Did I not type in the in here correctly?
You had to, because we all got 0 too.
Yeah.
I mean, yeah, I'm missing something here. What is the probability of obtaining this or more individuals? And I'm guessing if I did the same thing for the fewer, that would end up being the same thing. Yeah, what am I doing wrong here? I thought this was how you do all of this. The mean
Is it supposed to be CDF? Maybe it's supposed to be PD.
should be CDF. That shouldn't change the inequality. It's still normally distributed. What am I missing here? The square root of P, 1 minus P. That's the right formula. Minus P over lowercase n. The population whose size is that? How fun. Get to relearn this in front of everybody. How embarrassing. I was going to make this homework due Monday no matter what. So you still got a good while to do it. Okay. Just get that P hat is that. But they already gave us that. That is the proportion. This is fun. Okay, yes, I know that. Repeat that of that. Okay, gotcha. Probability of, oh, I'm so stupid. Okay, I forgot one. Okay, that's just a brain fart. I'm sorry. Okay, let's try that again. So I forgot this formula. That formula comes in handy. Okay, how embarrassing. What you wrote down is not, well, okay, it is wrong, so, but only up to there. There's one thing I forgot. You have to take, well, you have to find P hat by simply taking the 657 and dividing that by n. Actually, I'll write out the formula first. This was the very first formula that I wrote out. It was x divided by n. Well, guess what x is? 657. Guess what n is? Well, they gave us that as, if we just scroll up a little bit, 1460. What does that quotient come out to be? Probably something.
145.
That 0.45. Cool. Now we can, so that is going to be part of our inequality now. So we need to convert the frequency to the sample proportion, which is what we did. So now that we have this, then what we're looking at is the probability of when P hat is, so really we're converting 657 to its proportion. So now it's 0.45 or more. And that's what we shove into the inequality. So it's when this is greater than 0.45. Another indication of this is that the mean and the data value in our inequality should be fairly close to each other. That was one reason why I knew we should have been getting 0 based off of what we typed in, because the 657 is very far away from the mean of 0.42, which is very unlikely. So there was just one intermediate, or actually one initial step that I completely just forgot. I'm excited.
The lower would be 0.45.
Yeah, so you start off, the lower is 0.45. We still pick 10,000. And then everything else carries over, 0.42 and 0.0129. Because remember, we need the lower, which the lower and the upper are always based off of the inequality. So the lower based off of the inequality is 0.45. The upper is 10,000. The mean follows from part A, and same thing with the standard deviation. And that should give us 0.0102, I think the book said. So let's actually hope that we get exactly that. 0.45. I'm going to just go back to using 10,000. 0.010. What did it say? 0.0102. I mean, it's close enough, but my math lab's picky. So let's make sure we're doing this correctly. 82. 0.0102. We need to put more decimal values for the. I'm going to figure out one more thing here. What am I trying to do? I think in some problems it makes you round your standard deviation to a lot of decimal places. Might change things. I'm going to find that out right fast. Square root of 0.42 times minus 0.42 divided by 1460. I'm going to use that as the standard deviation for doing second and answer. It's closer. It's much closer. One more thing I want to try. I think this comes down to a rounding thing. I truly believe. I solely believe that this is a MyMathLab thing. I think they ask you to round to a certain number of decimal places. Let's go ahead and figure this out right fast. Let's figure this out all at the same time. Okay, I don't think it's that one. I don't think it's that one. Okay, I don't care. 6 decimal places. 6 decimal places. Let's keep that in mind. They want the standard deviation, 6 decimal places. 0.012917. And it's still 0.0101. I don't think of a margin of error. I can probably figure that out pretty quickly. Where are they getting that from? 0102. Preview. Okay. Six. Let's see if it comes up the same for the other one. I'm going to say that they want you to round. So I'm going to go back and say that 0.42 is 1 minus 0.42 divided by 1460. Add some extra decimal places, 17. And so with this slight modification, doesn't really change too much. CDF. We converted that to 0.45. And it was straight 0.45, no other decimals, right? Okay, cool. So that's, and then the upper, as we saw, the upper doesn't change anything. The mean is 0.42, which is not a computation, so that should stay the same, 0.012917. And I think we did all of this already. Just to make sure, 0.45, 10,000, 0.42, 0.012917. So the book seems to be off by literally 100 by 1/10,000th of a place. If this gives you any issues where you're off by literally the last decimal place, just shoot me an email if that happens, and I'll just give you the points because I can do that very easily. Let's see if that happens the same thing for the next problem, because I got the next part from the book as well. It says that the answer would be 0.0606.
So would you do it the same as what we just, like, would you do the 584 divided by 1460?
Yeah, so you still have to convert that to,
Instead of like the first one, that one would be the upper.
yeah, so that's going to be the upper. Let's see if this works out for this problem as well. So 584 divided by 1460.
It's 0.4.
Just 0.4? So just 0.4. Let's go right back to the probability of p hat. Now it says this or fewer, which changes our inequality. So fewer would be less than. Not that anymore. We converted that to 0.4. So this is not a z-score, by the way. 0.4 is not a z-score. It's just a proportion. If we did this using the table, we would have to convert this to a z-score. So this is equal to the normal CDF. So yes, the inequality tells us lower and upper. The lower, since this is less than, what's the smallest number less than 0.4? Well, there's not really a smallest number. Technically, negative infinity as an idea. So we could give it negative 10,000. 0.4 would be the upper, again, from the inequality. The mean and the standard deviation carry over. So again, the book says that the answer is 0.0606. What does the true answer come out to be?
I got 0.0608 if you round up.
See, my only issue is as
Instead of 0.4, and I got 0.0605.
let's see what I get. Because I would be perfectly okay with these stupid menial rounding errors.
But I did it ahead, and I didn't do negative 10,000. I did 0 as the lower.
Yeah, you have to go into the negatives as well, based off of.
But my answer is closer.
So it might have cut your answer off but very slightly. That's kind of the issue with some of the statistical stuff. Yeah, so I got what you got, 0.0608, which again, on a test, I wouldn't care at all if you're off by tenths, hundreds, 10,000, one 100,000ths of a place. I'm just curious, which the book, they might be doing it differently. I think my math lab would be consistent with any rounding that you do. But again, if it's not, and you find yourself off by literally one tiny decimal place, if enough of you shoot me an email, I'll just go through and just give you the points, because that, that's being off by such a little amount. He's doing something in this book that I'm not aware of that's slightly off, because I could change negative 10,000 here. Oops. If I change negative 10, that's the only other thing in this problem I can modify. And it doesn't change anything. So I'm going to just go with 0.0608. I wish I would have never looked at the book's answers. I bet we would have been none the wiser. But again, if you're off by a literal one decimal place, now if you're off by a tenth of a decimal place, that you're way off in this context. If you're off by a tenth, 100, 10,000, 1/100,000th of a decimal place, then just shoot me an email. I'll change that for you, and I'll probably go in and change everybody else's as well. if my math lab's being just extra nitpicky about it. Well, that was fun. So yeah, that was really fun. Every day I just get to figure out what the author's talking about over one decimal place. But again, at least we all saw this together, and you can all let me know if that happens. So, does anyone have any questions? We get to do another example as well, and this example I made up, so we'll have to kind of hope that these answers are just fine. On the bright side, there's only 6 questions on this homework. You can probably breeze through it pretty quickly. So, example 3. Let's go to example 3. After that small mishap. So, I went and found one of the Southeastern surveys, and so I would imagine any of you are started school in 2017. That would imply that you were probably a senior. I don't know if there's any seniors in here, but from the incoming class of fall 2017, there was a 51.9% retention rate for fall 2020. What this means is for people who started in fall 2017, are they still here or did they graduate by fall 2020? Which is telling us that about 48% of people roughly either dropped out or transferred. It's quite a lot of students. That's a lot of people, and considering we accept about 2,100 students each semester, each fall semester, it's about 1,000 people just right out the gate, right there. So Southeastern doesn't have the best retention rates, and this is a point of contention among statisticians. So let's say we pick a simple random sample of 600 students from this. The first thing they ask, I saw this in the homework, they ask, is the result of this survey qualitative or quantitative? And so the result of the survey, so it's basically the question that you're asking them and the result you get, is that a qualitative result or a quantitative result? Now retention rate, basically it's asking, are you still on this campus or not? Yes or no? So yes or no, is that a qualitative thing or a quantitative thing? Can you add yes to yes? Not in any realm I can think of. That's a more qualitative approach. It's going to be qualitative. So yeah, I saw this in the homework and I wanted to.
I don't understand how it's qualitative because if it's yes, it's a yes. I don't get that.
Because what?
You said it's qualitative.
Mm-hmm.
Well, why would it be quantitative?
Well, it's because, so it's the result itself. So what is the result that you're getting from the students? And it ultimately comes down to what a retention rate means. The result is, so I can figure out the retention about you. Basically, if I ask you, are you still a student here? What kind of answer would you give me? Yes or no? It's the yes or no premise that we are looking at in terms of qualitative versus quantitative. Is the answer of yes or no, is that qualitative or quantitative? That'd be qualitative because,
Overall, isn't it quantitative?
well, I mean, it depends. It depends on how you look at it. So let me ask another thing. So if I asked what your height was, you would tell me a number.
Right.
That would be quantitative.
Okay.
So that's kind of the distinction here. It's basically, what type of response are you giving me? Is that a quantitative response, as in, are you giving me a number that can be added or subtracted? Or are you giving me something that's categorical?
Okay.
That's the primary distinction here. This is a lot more interesting of a class to teach than college algebra, that's for sure. I like looking at these things in more conceptual perspectives. Qualitative, since results are pretty much yes or no. That's the way I look at it. Basically, are you a student? That's what they look at. Are you a student or are you not a student? So I just wanted to clear that one up if you saw that one in the homework. And then describe the sampling distribution of the sample proportion. So in other words, they want us to determine the shape. Is this approximately normal? So describe this. So they're asking, in other words, is P hat approximately normal? And I think they might even say that in the homework. That's basically what they're asking. And to find this, that's the two conditions that we have. One being n is less than or equal to 0.05 times capital N. And then the other one is NP1 minus P greater than or equal to 10. Now, what I find interesting here is, so I saw this in the homework, and I was kind of confused by it because they don't give us a capital N in this problem. But then when I tried to, this was a similar problem based off of something else I saw in the homework. They don't give a capital N in this problem, but somehow they are able to say that this is true. And the example in your homework just says it is true and doesn't prove why. I wasn't able to figure out a reason why. So I'm just going to assume that we're always going to get this condition because we're always going to have an approximately normal situation. Because if we didn't, then you couldn't do these problems. I have no other way to explain it other than, I mean, that's the first one's always going to be true. And I looked at it and I could not figure out a thing. But the book says, in this case, this just works. I don't know why. So just gonna assume that one's true. The other one is the one we can definitely figure out. That one's a lot easier because the probability is, of course, well, really it's the decimal version. So it'd be 0.519 because we have to convert it to a proportion. They gave us the percentage. Actually, why did I put that in place of n? Let me stay consistent. The n was the 600 students. The 0.519 is derived from the 51.9%. So that's 1 minus 0.519, and we need to show that that is greater than or equal to 10. (600) times 0.519 times 1 minus 0.519. So we get 149.7834, which is in fact greater than or equal to 10. So both conditions hold. Now, I think in the homework, they do ask for this number. They want you to state that number. So you just type that number in. But really, for every example, you should expect that we're going to get these two conditions to hold. Because if they didn't hold, then we can't use the normal CDF function in the calculator, which really renders the problem useless. But they will ask you to sort of justify it in this one particular situation right here. Just say, what number did you get to compare to 10? But once you figure out that, once you get approximate normality, we know that we can use the normal CDF function in the calculator. And with this, we need the mean and the standard deviation of the sample proportion. So the mean of the sample proportion is simply the probability. What's going on?
I put it in the wrong spot. Like I put it on an A, the A part.
Oh, gotcha. See, probability we get, what was that, the 0.519. The 51.9% is the probability, but they gave it to us as a percent. We normally represent percentages as decimals. And we can figure out sigma of p hat, which is the square root of, well, the p-value times 1 minus the p-value divided by n, which was 600, I believe. And so we can figure this out right fast. 0.519 times 1 minus 0.519 divided by 600. 0.203, and I think they make you round it to 6 decimal places. So I'm going to stay consistent with that. Give you a more precise answer for your proportions. 0.20398. Cool. And so once we have these values, we can quickly figure out these proportions using the calculator. What's the probability? So probability means we can use that normal CDF function. When it exceeds 54%. Now the interesting thing here is that they're already giving us p hat. Remember in the previous problem, we had to do the fraction, divide the frequency by the total number. But here they already did that for us. They're just saying, once you do that division, you get 0.54. So really we can jump straight to when p hat, and I'm gonna leave a little bit of space and something about 0.54. They're already doing the division for us. Now, if it exceeds 54%, it's gonna be greater than.
Oh,
You can redeem yourself in the next part, right? In part E. So this is the inequality we have. So with this inequality, we get 0.54 for the lower based off of the inequality. The upper is going to be, well, just give it 10,000, that's fine. The mean we have is 0.519. Standard deviation we found to be 0.020398. Put this in the calculator and we are done. 0.54, 10,000, 0.519, 0.020398. 0.1516. And while I'm at it, since we have about 2 minutes left, between 48 and 52, this tells us when we have a probability between 0.48 and 0.52, which works out nicely with the normal CDF function. 0.48, 0.52, and then the mean and the standard deviation. So I can go ahead and plug this into the calculator, retrieve the old information. That was 0.48. The other one is 0.52. Delete. And since we have a compound inequality, we don't need any use of a 10,000 because we already know they give us the lower and the upper. So 0.48, 0.52, and then the mean and standard deviation stays the same. And then finally, if 500 of 600 different samples were obtained, well, since we know that the probability is 0.4916, and there's 500 students that we selected, then that product would tell us about how many students we would expect. 0.4916 times 500 is 245.8, but students is a whole number. So we're going to round that to 246 because students are integers, whole numbers. And so that's a perfect place to end because I have nothing else for this section. This homework is going to be due Monday, so you have some time to do it. It's only 6 questions, so you can probably breeze through it or have already breezed through it concurrently with the class. So I am out of time. If you have any questions, shoot me an email. You know the drill. Sign the roll sheet if you missed it, and have a good day.